Chapter 12 is on the gas laws, or gases and liquids. Chapter 12, Section 1 discusses properties of gases. So gases are fluids, meaning their particles can flow, they have low densities, they're highly compressible, and whatever container that you put them in, they will exert pressure equally in all directions. And they're also influenced by temperature. So temperature determines the average kinetic energy of those gas particles. The kinetic molecular theory helps to explain the behavior of gases. It was developed in the mid-1800s and it's still useful today. Basically, it assumes that a gas is ideal, which makes up two parts. Collisions are elastic, meaning that if these particles run into something, they will not lose kinetic energy. And in the second part, it is the volume of individual gas molecules is negligible, meaning that in comparison to a total mixture of gases, the volume of one gas that's in that mixture is very, very small in comparison to the whole. The difference between elastic and inelastic conditions is, in reality, most collisions are going to be inelastic, meaning that like if you drop a ball, a bouncy ball, it's going to bounce about halfway back up, about halfway up from there, and so on until it's not going to bounce up at all anymore. If the collisions were elastic, then they would keep bouncing to the exact same height. The kinetic energy would be maintained. So if both of these things were true, then that means that the gas is behaving ideally. And an ideal gas is just describing the behavior of gases under most conditions. So not all conditions, but most. And they're most ideal at high temperature and low pressure situations. So high temperature and low pressure gases act more ideal. This is a reminder from the beginning of the year. We talked about the equation for kinetic energy, which is half mv squared, where m is mass and v is velocity. So kinetic energy is going to be determined by the temperature of a gas. The higher the temperature, the more kinetic energy those particles can have. Pressure is units of force divided by area. So the actual units you would measure them in would be newtons for force, and then pressure could be a Pascal, which is a Newton meter squared, so area would be in meters squared. We'll use pascals. The book uses kilopascals a lot, which is just 1,000 pascals. ATMs is a pretty common one. Atmospheres. Millimeters of mercury are used a lot, especially in like barometers. And then torr are another one. There's a whole table in your book that you can use to look up different pressure units. For gases, they have what's called STP, standard temperature and pressure. And these standard conditions are slightly different than the ones that we learned for thermodynamics. So for STP for gases, the temperature is going to be 0 degrees Celsius, which is 273 Kelvin, and pressure is going to be 1 atm, or 101.325 kilopascals. Now, I'm sure you've talked about the greenhouse before in biology class, and we're just bringing it up here because we're going to look at the actual chemistry behind it. With the greenhouse effect, it's just the increase in the temperature of the Earth that is caused by reflected solar radiation that gets trapped in the atmosphere. So the more greenhouse gases that there are, such as carbon dioxide and chlorofluorocarbons, things like old refrigerants and air conditioners, certain aerosols, they add to these greenhouse gases, which then traps more heat energy and causes global warming. So the actual chemistry behind that, you need to know what a free radical is. A free radical is an atom, or it can be a molecule, that has one or more unpaired electrons and is therefore very reactive. We know electrons like to be paired up. So what happens is UV light actually has the ability to break apart CFCs, or chlorofluorocarbons, and that liberates a chlorine-free radical, which is symbolized by the chlorine symbol and then a single dot representing that lone electron. That chlorine-free radical then rapidly reacts with ozone, or O3, to form this chlorine monoxide compound, oxygen gas, just regular oxygen, and a lone oxygen. Okay, and we know that oxygen doesn't usually appear by itself. It's usually diatomic. So this compound here, the chlorine monoxide, is very reactive, and so is the lone oxygen atom. And they will react with one another to form oxygen gas and more chlorine free radicals, which will then react with more ozone and cause this reaction to continue going. And that's called a chain reaction. It's self-sustaining. The products from one step act as reactants for the next step. And so one chlorine free radical has the ability to destroy thousands of ozone molecules.